Okay.
Okay. So our first and only paper for the debugging session will be automatic rollback suggestions for incremental data log solutions, presented by David Zhao.
Yep. Cool.
Okay, take it away.
All right. Thanks for that introduction, and thanks for those of you sticking around for this talk. Yeah, so I'm here to present this work on providing automatic rollback suggestions for incremental datalog evaluation. So this is some joint work with some colleagues. So Pavle's at Microsoft, Mukund's at University of Southern California. So to briefly introduce, I hope we all agree here at PADL that Datalog is an excellent logic programming language. It's had a bit of a sort of tumultuous history over the years, which I won't get into too much. But in the last few years, there's been quite a number of interesting modern use cases. So here's just a list of some kind of analysis style use cases. We've also more recently got applications in like database querying, analytics, and so on. And of course, in many other areas as well. So if we take, for example, program analysis as a problem, so this is obviously a very important problem for like compilation. So we can do optimizations, we can do security checking, and checking all sorts of other invariants and so on. And so one specific example of program analysis is what we call points to analysis. And so the idea here is that like when you define your program, we have variables and then they might point to some objects in the heap. And so our points to analysis will basically find relationships between these variables and objects. And sort of as a subproblem of this, we can also do an alias analysis where we check whether like two variables might point to each other, point to the same object in the heap. So sort of a typical workflow for these kinds of program analyses, for example, they might be deployed in your like continuous integration system. And then every time a developer like commits some new code to the repo, it would sort of change the inputs to the program analysis tool. So depending on sort of the new code. And then of course, we have these sort of modern techniques for Datalog or for program analysis in general, where we can do like incremental evaluation. And then so the idea is that will efficiently update the results of our program analysis given the like changes in the input caused by the commit. But then, of course, sometimes these commits might introduce errors, right? And so typically what we will do is then we kind of roll back or like revert the whole commit, and then we go and investigate our error that happened. And then we try and work that out. So the idea for this talk is like, is there a way that we can, like, instead of trying to revert the whole commit, like, can we find like a small subset of the commit that we can roll back? And that subset should be the one that like causes the error, right? So we want to find just the small part of the commit that actually causes the error. So let's look at like a concrete example. So this is maybe somewhat of a contrived example, but let's say we have some kind of like session management like application. We have like some admin sessions, some insecure sessions, and then like some variables that might point to these objects, right? And we want to run like a security analysis over our source code. And let's say we have some invariant that we wish to maintain that our like user session variable here should never alias with like sec, which points to our secure session, right? So so we want to maintain that no matter like what new code we introduce into this source code. And so what a program analysis might look like. So this is like a points to analysis written in Datalog. So essentially, each of these Datalog rules represents like one type of statement in our source code. So the first rule says like if we have some new object, then that represents like a heap object. And then if we have a variable equals new object, then that variable might point to that object. The second one is like an assignment statement between two variables. And then this last rule says like if we have two variables that point to the same object, then they might alias. So then how we would run our program analysis is we take our source code, we run it through some kind of like extractor, they usually call it. And so in this case, there's a very simple extractor. It just essentially transforms each line of our source code into one tuple that is input for our program analysis. So to give a little bit of background about how this would work in practice is, so the standard Datalog evaluation strategy that we typically use is bottom up. So we start from our inputs, in this case, which represent the program we want to analyze. And then in each step, we apply all of our Datalog rules until we reach fixed point. Right? So in the first iteration, we have our inputs, which just get transferred into the, so VPT stands for variable points to here, so into our points to relation. And then we can run the recursive rules. And then we can generate the alias relation until we reach fixed point. So this is a typical sort of bottom-up evaluation. And then so there's a bunch of new developments in this area of incremental evaluation. So so this is becoming sort of more and more popular of a field of research where we want to sort of efficiently update the result of our Datalog program given some changes in the input. So I'm not going to go into a lot of detail about how this works, but sort of the basic overview is that we need to keep track of how tuples are derived during our Datalog evaluation. And how this works is that we want to keep these annotations for each tuple that is computed during our Datalog evaluation. And these incremental annotations essentially represent, one, the number of different ways to derive that particular tuple, and then two, kind of a timestamp or which iteration in our bottom-up evaluation that tuple is computed in. So using these two annotations, then if we insert or delete an input tuple, we can sort of keep track of where that comes from, and then we can efficiently update any tuples that depend on our input that we changed. Cool. So for example, back to our sort of session management application. So let's say we kind of add a bit of new code here, which you can upgrade some user session into an admin or something like that. Then the implications for our program analysis is that we would insert these two new input tuples. So again, here each tuple represents one line of our input. But in this case, we actually end up violating our invariant. So what happens here is we had our existing tuple, which was a store into some field. So admin equals session.secure. And then we introduced our new tuple, this load tuple here. And then together, using the load store rule in our program analysis, we would end up with this alias where user session might point to the same object as our secure variable. So this violates our invariant, and then so we want to try and fix this error. So this leads into the main part of this talk, which is these rollback suggestions that we try to compute. So to recap, so we inserted these two new tuples. We ended up with an error. So we inserted this new tuple alias user session sec. And so we want to provide a rollback suggestion, which we define as kind of a minimal portion or subset of our incremental update, which caused the error to be produced. So in this case, actually, so even though we inserted these two new tuples, only one of them is actually relevant for the error, right? So the other tuple is not relevant for producing the error, so we shouldn't need to roll back the whole commit. So so this is a little bit of a detour into the land of provenance, and I'll explain later on how this connects back to our rollback suggestion problem. So provenance, which was sort of a technique that we developed a couple of years ago, essentially is a way to show how any output tuple is derived through the program. So if we take this tuple, the user session points to L3 as an example. We have the system which can generate these proof trees automatically. And then so through the proof tree, you can see which input tuples are involved and then which rules are involved in generating our output tuple that we are interested in. So in this work, we care about what happens after an incremental update. So we kind of introduce this notion of an incremental provenance. And so incremental provenance will show the changes in our proof trees after an incremental update. So if we look at our error tuple that we're interested in, the incremental proof tree for this shows kind of which parts of the proof tree are newly inserted, which result in this error tuple being produced. Right? So importantly, like all the gray ones on the other side, the gray tuples there, so they were already existing in our input, so they haven't changed as part of the incremental update. And then these like black tuples with the plus label, these are the tuples that are newly inserted during the incremental update. So when we want to roll back the parts of the update which cause the error, the idea is that we essentially want to disable all of the ways to compute our error tuple, right? And so there's incremental proof trees that I showed before. So each proof tree shows, or it represents like one way to compute the error tuple. And so a rollback suggestion is essentially just a subset of the changes so that we disable all of our incremental proof trees, right? So if we disable all ways to derive the tuple, then it should no longer exist, and so our error will disappear. So in this example, so obviously the input tuple that appears in our incremental proof tree, this is the relevant tuple for our error, and so if we roll this back, in other words, we delete the tuple that we just inserted, then the proof tree is no longer valid, and then so we will have fixed the error. So in this case, our rollback suggestion would just be this one tuple here. So clearly, this incremental provenance problem is quite fundamental for our rollback suggestion problem. And so going back to this paper from a couple of years ago, the approach that we had there for computing provenance was we had this kind of two-stage idea, right? The first stage is we evaluate our Datalog program, bottom up as usual, and we annotate every tuple with these provenance annotations. And then in the second stage, we let like the user query. So the user can say like explain some particular output tuple, and then the system will use these annotations that we computed to produce the proof trees. So we observed that if we have an incremental evaluation system, then we also have these incremental annotations. And it actually turns out that these incremental annotations essentially keep track of how tuples are produced in a very similar way to how our provenance annotations work. So if we have an incremental Datalog system, then we get this ability to compute our proof trees efficiently almost for free, right? We just use the same annotations that incremental evaluation requires. So okay, so now that we have our like incremental provenance system, how do we go back to rollback suggestions? So we have kind of two different cases. So the first one is if we have one proof tree, then obviously like any part of this proof tree that we can disable will disable the whole proof tree. So any sort of singleton like input tuple could form a valid rollback suggestion. So so any of these works. And then the second case is if we have multiple proof trees, right? So multiple proof trees, we like a tuple could be derived in many different ways, and so we want to disable all of the possibilities of how to derive this tuple. And so we have this problem where we want to find like a minimal set of the inputs such that we can cover all of our proof trees that we want to disable. So we called this kind of a minimum proof tree cover problem. And our approach to solving this was to use some kind of integer linear programming. So it's kind of an optimization problem. We want to find like a minimal set of inputs that cover all of our trees. And so our encoding for the integer linear program, we have a few constraints. The first one is we want to maximize the number of input tuples that we keep. So this is, of course, equivalent to disabling the smallest number of inputs. The second set of constraints, we want our integer linear program to encode kind of the semantics of the proof trees, where kind of like every line in the proof tree will derive like the child. And the last one such that our error tuple is not computed, right? So we want to disable our error. And so this is kind of what our linear program looks like. So the optimization is to maximize the number of inputs that we keep. The second line is essentially encoding, like every line of the proof tree will get a constraint such that we disable our error tuple. Right. And so once we solve this integer linear program, yes. Oh, sorry, I can't quite hear. Yeah.
Why do you need to encode the proof trees in the program? It seems like just deleting any of the leaves.
Yeah, so in the case where we have like multiple proof trees, for example, like if we kill, let's say like T2, then we would kill this proof tree, but then there might be like another way to derive the tuple as well, right? So we kind of have to cover all of our proof trees so that we disable like all different ways to derive the tuple, right? Yeah, it's a good question. And yeah, so the other reason why we needed to encode the proof tree semantics is like, this could also be like a minimum set cover problem. Like we just take the inputs as sets and then try and cover all the trees. But it turns out like if we have negations and deletions and so on, this gets quite tricky. So we actually need to understand the semantics of the proof trees in our integer linear program. So yeah, so if we solve this, then we can cover all of our proof trees. And so yeah, so using this, we have our solution. And in the paper, there are kind of like other important Datalog features that we can support as well. I'm not going to go into full detail here. But the first one is the being able to delete tuples. So of course, incremental evaluation, we can insert new tuples, but we can also delete tuples. And so this could also be an error that we're interested in. And the key idea here is we basically treat our incremental update in reverse. So obviously, if in one direction we delete a tuple, then if we look at it backwards, then we would be inserting that tuple. So we look at our update in reverse, and then it's essentially the same problem again. And of course, stratified negation is also a very important part of Datalog semantics. And so the idea with stratified negation is like if we have an insertion of a new tuple, let's say we insert into the predicate that is negated in this rule, then this could lead to like new tuples being, this could lead to existing tuples being deleted because we're like changing the negation constraint. And so, yeah, so the idea is that we can actually treat our negation similarly to how we treat deleting tuples. So we just look at the reverse direction of our incremental update. And then we can do this like strata by strata, right? And because we have like a finite number of strata in our program, then we get like termination of this whole process. So now onto these some experiments that we had a look at. So we implemented our rollback suggestion system using Soufflé. So there is a kind of a prototype of incremental Soufflé, and we use that. The actual algorithms for this rollback suggestion system were implemented just in Python. So they just look at the output tuples that are produced by Soufflé and the proof trees that we get, and then does some manipulation in Python. And then we use this like library for solving integer linear programming in Python. And we compared against this approach called delta debugging. So delta debugging is it's a very old approach, and it's very general. So it applies to any kind of sort of error minimization problem. And it's essentially a divide and conquer approach. So we take our whole incremental update, we just split it in half, and then run each half separately to try and narrow down the part of the incremental update that causes the error. The benchmarks that we used was this Doop program analysis framework. So this was this is a framework where we do pointer analysis of Java programs. And yeah, so for each benchmark, we just choose kind of an arbitrary incremental update set, and then we run our debugging algorithms. So our results look something like this. So in general, our like incremental rollback suggestion system is kind of an order of magnitude faster than the existing delta debugging approach. And the main reason is because delta debugging, like we split our inputs in half, and then we kind of have to run each half separately. When we have like a big program like Doop, each run can take quite a long time. And so using our incremental system, where we just produce proof trees and then run an integer linear program, turns out to be, in most cases, a lot faster. So there is, of course, one outlier, this bloat program, where incremental is slower, and this is because the ILP that's generated is actually really big, because the proof trees were really big in that case. And so that took a long time. But overall, our system is quite a bit faster. So in conclusion, we've seen that Datalog is very useful for program analysis tasks, and we have these new techniques like incremental evaluation, which can efficiently compute changes. But these incremental updates can, of course, cause errors. And so this technique allows us to find these small subsets of the update, so we don't have to roll back the whole update. We can just find like a small portion of the update. And of course, I want to point out that while I use like program analysis as an example to illustrate how all this works, this technique is in principle applicable to any Datalog program that we might have. It's cool. Thank you.
Okay, I'm going to open the floor up to questions.
Hey, do you have a way of mapping these rollback suggestions back to source code? Like if I'm in CI, it'll be like, hey, delete this line of code.
Yeah, that's a very interesting question. So the answer that we have to that is that, like, generally when you have an extractor for the program which maps it into input Datalog tuples, like the extractor might keep some mapping information between like which inputs come from which source code, which parts of source code. So if we have that kind of thing, then you'd be able to map it back. But yeah, it kind of depends on the extractor and the whole like framework for program analysis.
You mentioned that you compute all proof trees, and do you have those proof trees available, always available? Do you have to compute them? Maybe you have one or some, and then you have to compute the others, or you have all of them available when you start the repair?
Yeah, so the proof trees are they're computed like on demand. So if the system says, so if you as a user say like this particular tuple is an error and we want to roll it back, then we go into our Datalog engine and we say, okay, give me the proof trees for this particular tuple, and then it will produce the proof trees like depending on demand. So the proof trees are not computed like eagerly during Datalog evaluation, but it's as like a step afterwards, depending on what the user asks for.
I see. But would it be possible to apply your method for eliminating all the proofreads you have found currently, and then maybe run again the procedure later if you find that the property is violated as well?
Yeah, for sure. Yeah. So each step is like, so you still have the Datalog instance like running in the background. So you could ask for like proof trees, and then you can say like, okay, let's like based on the answer, like let's do some incremental update, and then you could like run like this rollback suggestion again, or yeah. So it's all kind of running in the background, and you can keep querying the system.
I see. Thank you.